Introduction. Students, as we all know that fertilizers are widely used in modern-era agriculture. Fertilizer use has been shown to be very effective in means of increasing agricultural productivity. About 40% of world protein production is based on synthetic ammonia. To meet high demand of ammonia, it is manufactured on large scale by Haber's process. The Haber's process combines nitrogen with hydrogen into ammonia. Nitrogen is an important element in P block in the periodic table. So students, today we'll study about the P block elements. Objectives. At the end of this lesson, you will be able to define P block elements, familiar about group 15 elements, know properties of group 15 elements, analyze anomalous behavior of nitrogen, explain properties and uses of dinitrogen, explain properties and uses of ammonia, understand oxides of nitrogen, explain properties and uses of nitric acid, describe allotropic forms of phosphorus, explain halides and oxides of phosphorus. Definition. Elements of group 13 to 18 of the periodic table are collectively called P block elements. Boron, carbon, nitrogen, oxygen, fluorine and helium head the groups. The general electronic configuration of these elements is Ns2Np126. They involve the filling of p orbitals of their outermost shell. The maximum oxidation state shown by a P block element is equal to the total number of valence electrons. This maximum oxidation state is called the group oxidation state. Group 15 elements, the nitrogen family. The elements nitrogen, phosphorus, arsenic, antimony and bismuth constitute group 15 of the periodic table. The first two elements of this group, nitrogen and phosphorus, are non-metals. The next two, arsenic and antimony, are metalloids. The last element, bismuth, is a metal. All the elements of this group have 5 electrons in their valence shell. Their general valence shell electronic configuration is Ns2Np3. Physical properties of group 15 elements. Atomic radii. It increases with increase in atomic number. Melting point and boiling point. These increase on going down the group. However, the melting point of bismuth is usually low. This may be due to more tendency of bismuth to form 3 rather than 5 covalent bonds. Thus, there are weak forces of attraction between their atoms in solid state responsible for its low melting point. Density. The density of the members increases down the group. Ionization enthalpy. The first ionization enthalpy decreases regularly down the group due to increase in the size of atoms and screening effective of intervening electrons. Repeat. And screening effect of intervening electrons. General characteristics of group 15 elements. Catenation. The elements of group 15 also exhibit catenation. Nitrogen forms chains extending up to 3 atoms. Phosphorus shows a distinct tendency for catenation, forming both cyclic and open-chain compounds containing several phosphorus atoms. Allotropy. Except nitrogen and bismuth, all other elements of the group show allotropy. Phosphorus exists as white, red, and black phosphorus. Arsenic exists as yellow and grey. Antimony exists as yellow and grey. Electronegativity. The electronegativity value decreases down the group with increasing atomic size. Oxidation state of group 15 elements. All the elements of this group have 5 electrons in their valence shell. These elements require 3 more electrons to acquire noble gas configuration. But gaining of 3 electrons requires a large amount of energy. It takes place only with nitrogen, as it is the smallest and the most electronegative element of this group. The other elements of the group form covalent compounds in which their formal oxidation state is -3. The elements of this group also exhibit +3 and +5 oxidation states, but they cannot form M5+ ions due to the large amount of energy required. Most of the other compounds with +3 and +5 oxidation states of these elements are covalent. In the case of nitrogen, all the oxidation states from -3 to +5 are possible. Anomalous behavior of nitrogen. Nitrogen differs from rest of the members of the group due to its small size, high electronegativity, high ionization enthalpy, non-availability of d orbitals. Nitrogen has the unique ability to form pi-pi multiple bonds with itself and with other elements like carbon, oxygen having small size and high electronegativity. Thus, nitrogen exists as diatomic molecule with a triple bond between the two atoms having high bond enthalpy 941.4 kJ per mole. Single nitrogen-nitrogen bond is weaker than single phosphorus-phosphorus bond because of higher inter-electronic repulsion of the non-bonding electrons owing to the small bond distance. Hydrides of group 15 elements. All elements of group 15 form hydrides of the type MH3. Structure. All these hydrides are covalent and involve sp3 hybridization. 3 of the 4 sp3 hybrid orbitals overlap with 1s orbitals of 3 H atoms to form 3 MH sigma bonds, while the 4th hybrid orbital contains lone pair of electrons. The bond angle decreases down the group. Basic character. Due to the presence of lone pair electrons on the central atom, these hydrides act as Lewis base. Electron density around the central atom decreases down the group. Hence, the basic character of these hydrides decreases down the group. Thermal stability. The stability of these hydrides decreases down the group. This can be explained in terms of their bond dissociation enthalpy, which decreases down the group. Boiling point. The boiling point of these hydrides first decreases and then increases down the group. The variation in boiling points is due to hydrogen bonding and van der Waals forces of attraction. Oxides and halides of group 15 elements. Oxides. All members of the group generally form oxides of the type M2O3 and M2O5. the acidic character of the oxides decreases down the group. N2O3, P2O3 and As2O3 are acidic in nature. Sb2O3 is amphoteric in nature. Bi2O3 is basic in nature. Halides. These elements react with halogens to form two series of halides: trihalide and pentahalide. Trihalides of these elements, except those of nitrogen, are stable. Nitrogen does not form pentahalide due to the absence of d orbitals in its valency shell. Pentahalides are more covalent than trihalides. Dinitrogen. Dinitrogen constitutes about 78% of air by volume. Relatively little nitrogen is found as compounds. Some preparation methods of dinitrogen are the following. Dinitrogen is produced commercially by fractional distillation of liquid air. Liquid dinitrogen with a lower boiling point, 77.2 Kelvin, distills out first, leaving behind liquid oxygen. In laboratory, dinitrogen is produced by warming a concentrated solution of ammonium nitrite. Dinitrogen is collected over water. Dinitrogen can be produced by heating a mixture of NH4Cl and potassium dichromate. Very pure nitrogen is obtained by heating sodium azide or barium azide. Properties of dinitrogen. Dinitrogen is a colorless, odorless and tasteless gas. It is relatively insoluble in water. It is a non-poisonous gas. It neither burns nor supports combustion. It is chemically inert at room temperature, but its reactivity increases rapidly with an increase in temperature. At very high temperatures, nitrogen combines with some of the more active metals to form nitrides. At very high temperature, nitrogen combines with nonmetals. Uses of dinitrogen. The important uses of dinitrogen are the following. It is used in canning foodstuffs. It is used in manufacture of NH3 and calcium cyanamide. It is used as a refrigerant to preserve biological materials and in cryogenic studies. It is used to provide inert atmosphere in welding. Ammonia. Ammonia is present in small quantities in air and soil where it is formed by decay of nitrogenous matter. In laboratory, ammonia is obtained by heating an ammonium salt with an alkali. Ammonia is dried by passing over quicklime. On a large scale, ammonia is manufactured by Haber's process. The Haber's process combines nitrogen from the air with hydrogen derived mainly from natural gas into ammonia. The reaction is reversible and the production of ammonia is exothermic. A pressure of above 200 and temperature of 700 Kelvin and the presence of catalyst favors the formation of ammonia. Properties of ammonia. It is a colorless, pungent-smelling gas. In the solid and liquid state, it is associated via intermolecular hydrogen bonding and has higher melting and boiling points. Due to the presence of lone pair of electrons on the nitrogen atoms, it is a Lewis base. It has a trigonal pyramid structure. N is sp3 hybridized and the bond angle is 107 degrees. It has 3 bond pairs and 1 lone pair of electron. It is highly soluble in water and is weakly basic. It can form coordinate covalent bond with the transition metal ion and form complexes. Uses of ammonia. The important uses of ammonia are the following. It is used as laboratory reagent and solvent. It is used in industry to manufacture fertilizers. It is used for nitriding of steel to produce very hard surface. Liquid ammonia is used in refrigeration. Oxides of nitrogen. Nitrogen forms a number of oxides in different oxidation states. Nitrous oxide or nitrogen 1 oxide. It is prepared by cautiously heating NH4NO3 or a mixture of NH4Cl and NaNO3 to about 500 Kelvin. Pure N2O is obtained